My name is Keith Heiger, and this is my final presentation for Dynamic Systems on artificial blood vessel design. A blood vessel is anything that moves blood inside of the human body. With this description, we could have chosen any blood vessel in the human body, whether it been like arm, leg, your throat, or your aorta in your heart. I personally chose to use the femoral artery. There are a variety of different reasons why I chose this. Um, It's the artery inside of the leg, and it pumps a lot of blood to your legs. Because of this, there's a lot of material that can be used to research and find different specifications for the artery. It's a very large size and has a very large flow rate. The specifications I was able to research and find was the inner diameter I found to be 9.8 millimeters on average for an adult male, using Stengren's paper that he wrote with his colleagues. The wall thickness I found to be 0.68 millimeters, and this was written by Smiled. I chose to find a wall thickness simply because each blood vessel is going to have a different wall thickness, and I wanted to specify that if I was to match it accurately with a material, just in case there was going to be a stress or a pressure issue. The wall thickness of the femoral artery is going to be really thick simply just because there's such a high volume of blood flow through this artery. For the flow rate, I found it to be roughly 284 milliliters per minute, in an article written by Holland and his colleagues. This is a flow rate of an adult male that is before exercise. So it's a resting heart rate blood flow. Then I needed to find 3 different biocompatible materials, and using Redding's plastics, I found PEEK, polyethylene, and PTFE nylon. I've personally used polyethylene and nylon before, not in a biocompatible criteria. However, I've never heard of the PEEK material, or it's a plastic, and I needed to do some research on that one simply because I'd never heard of it, and it is generally specifically for biocompatibility. That's what it was designed for. I chose to use plastics over metals simply because in the leg, it needs the flexibility. It needs to be able to move around. Whereas if you just have essentially a metal straw in your leg, it'll be very uncomfortable if it gets bent or crushed or in trouble. Whereas a plastic, it's going to be able to flex and it's going to be able to take some compression and then regain its initial size. So from the previous specifications on this slide before this one, I started my initial design for SolidWorks using the inner diameter of 9.8 and then the wall thickness of 0.68. We then needed to create 3 different lengths for each material. And so we needed a 1 millimeter length as seen on the right. We needed a 10 millimeter length as seen on the top. And then we needed a 100 millimeter length as seen on the bottom. Then we needed to simulate them. So for using a PEEK, for the PEEK material, and I took the flow rate of 284 milliliters per minute, and I had to translate it into millimeters cubed per second for flow rate for SolidWorks. And for at that resting heart rate flow rate, it was 4,734 millimeters cubed per second. After this, I simply just inputted the data into each one of my drawings and found a velocity flow rate. I chose to do velocity simply because it's the best. It has the best visual aspect to it, and I knew that it would show nice lines. However, the main data is going to be in the chart, which I found from each of the simulations. So on the left, it's the 1 millimeter wide tube. On the top, it's the 10 millimeter wide tube, and it's showing both of those, actually all 3 of them on the 100 millimeter on the bottom. All 3 of them have the same velocity of 63 millimeters per second. And on the bottom, as you will see on the other ones, I discovered that on this top, the 10 millimeter and the 1 millimeter didn't have a change in velocity, whereas at the 100 millimeter, it hits a length of about 50 millimeters. You start to see it to slow down at about 75 millimeters. It's really slow, which isn't going to be accurate in a body, in like the human body, simply because the heart has a constant rate of flow going through it. So it's not going to be slowing down. But in the simulations, these are the results that I was able to get. And from this simulations for the peak, I came up that it had a velocity of 63 millimeters per second. It had a pressure of 0.101325 millipascals, which, as you will see going through this, I had the same results for every single simulation at this flow rate. These are the polyethylenes. They look identical, but they are a different material in my SolidWorks. That's just the color that SolidWorks gives polyethylene and peak. And as you can see from the drawings, the same flow rate happened, the same velocities happened for polyethylene as peak, with the max velocity